Hi, everyone. Now in our last video about straight hydrocarbons, we're going to talk about what happens when we don't have a simple straight chain, but when we start to have different things coming off the chain at various places. A branched chain hydrocarbon has one or more of the hydrogen atoms that would be along its main chain substituted with some other carbon branch. The root name is still always going to be based on our longest continual carbon chain. And you can see it's a reminder of all those below, all those root names there. And so let's just take a look at what I mean by a hydrogen atom is being substituted. And so let's say we have just maybe pentane. So 1, 2, 3, 4, 5. And so drawing in the hydrogens, which again, we normally don't do with a skeletal drawing, but just to draw those in for the purposes of showing you what we mean. So there's all of our different hydrogens. And so what we're going to do is we're going to go ahead and replace one of these. We're going to go ahead and replace, let's just say this hydrogen here for the example. We're going to replace that with another carbon chain. And so now we're still going to have our methane, but now one of those hydrogens is now replaced by a carbon chain that's 2 carbons long. And so this is what we mean by a branched chain. And we don't necessarily have to stop there. We could certainly replace both of these hydrogens with other chains. We could do something like this and add that on there. We could also replace one of these, and maybe we have this. And so the possibilities would be endless. We could even have another one coming off here. We could do something like that. And so that's really the focus of today's video, is looking at the effect that might have on properties, but also really looking at, and a big part is looking at how we go on now to name compounds like that start to have things branching off of our main chain. And so an alkyl substituent is, again, something that substitutes for what would normally be a hydrogen in a straight chain hydrocarbon. The root name, and I know that I said this a lot, but this can't be stressed enough. Our root name for the compound is still going to be based on the number of carbon chains in our longest continuous chain. Now, and we'll see some examples of this. When you're looking for that longest carbon chain, it's not always going to be simply right to left. Left to right. It might be right to left. It might be up and down, depending on how the thing is drawn. We might have a compound that looks, we might have something like this, but then we might have coming off here, we might have that. And so it's tempting to look at something first and say, okay, well, I'm just going to go from side to side here, and I'm going to say that I've got 1, 2, 3, 4, 5, 6 carbon atoms, so there's my longest chain. Don't do that. Look for however this thing is drawn and what the longest chain would be. And so we could see here that our longest chain would actually be right here. And so we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons long. And so our root for this would be dec. So always look for that longest carbon chain, however you have to go, whatever route you have to take to get there. Look for what the longest continual chain is. And that's called the parent chain. And so your root and your ending are going to be the same as the root and ending that we've talked about so far, either ane, ene, or ine, depending on if it's an alkane, alkene, or an alkyne. But now we're going to start to look at a lot of the prefix, and the prefix will be something that we insert in the front before the root to indicate the substituents, to indicate the things that are hanging off the main chain and where they are. Again, just a reminder of our straight chains and our names for those. When we're writing condensed structures for main chains, we write the sequence for the carbons in the main chain. We now will also show the branches, which are occurring at either CH or Cs, and those branches might be above or below, depending on how the compound is drawn. And we're going to write the branch with its own sequence. Let's take a look at an example, a little easier to see that. So the name of this compound, 2-methylbutane, we're going to look at these naming rules. But we have 1, 2, 3, 4. So there's our root. There's our longest carbon chain right here. And yes, you could also say the longest carbon chain is here. Same either way, because it's the same group hanging off at the same location. And we'll see more about what that means later. So here's our main group, but now we have a branch point coming off that. And so two different ways that we might draw that condensed structure. We might draw it like this. And so again, we can see our branch point with the CH3 coming off. And so in this case, if you're drawing using this convention, you would draw that bond in there. Sometimes we also use parentheses. And so we can see here, here's the CH3, there's our first CH3. Here's the C, that's our branch point, that's the CH. And these parentheses here, without any subscript, just these parentheses, this now indicates that that's a branch coming off our main chain, then followed up by the rest of the chain here. Another example here, 2,2,5 trimethyl-octane. Again, don't worry about the naming. We'll be looking at those. But here's our main chain, 1, 2, 3, 4, 5, 6, 7, 8. So there's octane. But we have these two different branch points. Here at the second one, we have 2 of these CH3s coming off. So we can see those here. Here at our 5th carbon, we have 1 CH3 group coming off. So we see that here. We might also draw it like this. And so there's the CH3 and the CH3 coming off our 2nd carbon in parentheses. Here's the CH3 coming off our 5th carbon in parentheses. And so that's just how we would draw the condensed structure. If we're drawing a skeletal structure of this one, then that would simply look like this. We have octane. And so we're going to have 1, 2, 3, 4, 5, 6, 7, 8 carbons long. And we would draw that just as there's one CH3 group, there's another CH3 group. So that's just these two groups right here. And then off our 5th carbon, we have another CH3 group. And so this would be our skeletal representation of this compound. Let's look at our guideline for naming. So the first thing we're going to do is always name our main chain. So find your longest continual carbon chain, and that's going to form our root. Now, if it's an alkene or an alkyne, if there's a double or a triple bond in there, now we need to set our longest chain as the one that contains the carbon atoms in the double or triple bond. Even if there is a longer chain somewhere else in the molecule, if it's an alkene or an alkyne, our root has to include our double or triple bond. It might be possible that there might be 2 main chains with the same number of carbon atoms, depending on what path you take through the compound. If that happens, then your root, your main chain, is going to be the one that has the greater number of substituents, the greater number of branches coming off it. Let's look at examples of both of those. So here we have this compound here. Now we could either name this 1, 2, 3, 4, 5 and give it the root pent, but we can see if we do that. So looking on this one here, if we number it like this, now our main chain does not include our double bond, and it has to. So our main chain now is going to include our double bond, 1, 2, 3, 4. Say it would be the same compound going the other direction, 1, 2, 3, 4. And now what we do is we name this substituent. We name this branch coming off it. So here's our main chain here in pink. And this is our branch coming off. And we're going to talk about how we name that. But this would get the full name 2-ethyl-1-butene. In the case like this, pretty complicated molecule here. But if we're looking at our longest chain, we could have our longest chain going from this stretch or this one, same either way, 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. So if we go this way, we have 7 carbons. If we go this way, we have 7 carbons. And if we go this way, we have 7 carbons. So which one do you pick for your main chain? You would not pick this one because this one only has one spot where it's got a branch coming off it. These two are identical. And again, we'll see why as we really get into the meat of naming. But these two would be considered the same. And so we would choose either one of these because these have 2 different carbons where you would have branches coming off. And so you would choose one of these to be your main chain with an eventual name of 3,3-dimethyl 4-propylheptane. And again, we're going to see where those names come from. So don't worry too much about the name right now. We're just focusing on how we would choose the main chain. After choosing your main chain, now we need to name the substituents. We need to name the branches that are coming off the chain. Substituents are named the same way that we name parent compounds or the root compounds, but now we add a YL suffix. And so we can see that here. And so we can see a main chain of 1, 2, 3, 4, 5, 6 carbons. So we get the root name hexane. We can see that these 2 branches coming off, these are both made up of just 1 carbon. And so again, if we sort of translate from the skeletal to a Lewis structure, just to see what that would really look like. So there's our skeletal structure. I'm not going to draw in all the hydrogens, but if we draw in just right in the carbons at least, it would look like this, and we would have those C's coming off. And so we can see that each of our branches here are made up of just 1 carbon. Each one of them separately are made up of 1 carbon. 1 carbon, remember, gets the root meth. But now that they're substituents, now that they're not main chain, they're called a methyl substituent. The next thing that we need to do, and I'm just going on to see, okay, I couldn't remember if I talked about more of that now or not. The next thing that we need to do is identify where those substituents are located. And so we can see here that the substituents, in this case, are located on the 2nd carbon. Now, this is not only just 1 methyl coming off the 2nd carbon, it's 2 methyls. And so dimethyl. And so we get we get dimethylhexane. And this 2,2 tells us where those methyls are. They're both coming off our 2nd carbon. Let's look at actually a bit of a simpler example than this one. So if we have just pentane, 2, 3, 4, 5, yep, there we go, there's pentane. We're going to put a carbon right here, a substituent coming off it. So again, here's our main chain. So we get the root pent. It's an alkane. So we get pentane. We're going to number it 1, 2, 3, 4, 5. We have a methyl group right here. Actually, I'll do that in red, get fancy. There's a methyl group coming off it. And it's coming off it at the 2nd position. 2-methylpentane. And there actually wouldn't be a space there, although it looks like one just the way that I drew it out. So there's no space there. There's 2-methylpentane. Now, it would be the same name. It would be the same exact compound like this. Remember, we're going to number in such a way that we end up with our lowest numbering system. So now we would number this 1, 2, 3, 4, 5. Because those are just mirror images of each other. Same compound, just a mirror image. We could have more than one prefix or more than one substituent coming off. Say I have this, and let's say I've got this coming off here, and maybe this coming off here. Let's throw one more carbon here for the heck of it. There we go. So now I'm going to find my longest chain. That longest chain is going to be here. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 carbons long. So I'm going to have oct for my root. It's an alkane, so octane. Now I'm going to look at my numbering. I want a number starting from this side because that's going to get me to my lowest numbers. And I can see that I have a methyl at the 3 position. I'm just writing these off to the side for now. You'll see why in a second. Methyl at the 3 position. I also have 1, 2, 3. This is a propyl group. At the 4th position. Now, when we're putting the full name together, it worked out this way this time, but when you put the full name together, you write the substituents alphabetically, not in the number order. And so this one, again, this one works out the same either way, but that means that this one would be 3-methyl 4-propyl octane. Now, if those were opposite, let's say instead, let's do this. So we'll go with our 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to go with a 3. We'll go with a 3-methyl. And on 4, we're going to have an ethyl group. So same idea. Oct, it's an alkane, so we get octane. We have a 3-methyl. We also have a 4-ethyl group. That's this one right here. 2 carbons long in the 4th position, 4-ethyl. So now, when we look to add our prefix, again, we're going to go in alphabetical order of our substituents. And so the actual name of this one is going to be 4-ethyl 3. Ran out of room there. 3-ethyl, or sorry, 4-ethyl 3-methyl octane. Note that I also put dashes in between any numbers. And so 4-ethyl. Then we're going to come up with another number. So -3-methyl. Those are an important part of our naming system as well. And so this is a lot of, sorry. So now going on to look at substituted alkenes or alkynes. Same idea. But again, now we're going to, our longest chain is going to contain both atoms as our double or triple bond. But then we use the same sort of numbering convention and same sort of naming convention for our substituents. Then we also have to use the cis-trans prefix if appropriate for any of our alkenes. Let's look at an example there. Say we have this compound right here. So we're going to find our longest chain that contains our double bond. It's going to be right here. And we see that is 1, 2, 3, 4, 5, 6 carbons long. So our root is going to be hex. It's an alkene. So it's hexene for our ending. Now we could either number 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So it's the same numbering either. Hold on, just let me check something real quick. Okay, sorry about that. And so we're looking at our numbering. And so again, so with this one, we could go either way as far as our double bond. It's still going to be after 3. But we want to start our numbering over here. Because that would ultimately put our substituent at a lower number. So we're going to start our numbering there. And so our double bond is after the 3rd carbon. So we're going to get 3-hexene. Now we look at naming our substituent. We have a methyl group coming off the 3rd carbon. And so 3-methyl 3-hexene. Sorry, I realized you couldn't see some of that, so I just made the screen a little shorter here, a little smaller. We now do have to worry about the cis-trans designation as well. So let's take a look at that. Let's see if I can erase some of this without really messing things up here. Not easily, it looks like. Yeah, a little bit. Okay. And so let's just take a look at that, at the cis-trans designation. And so remembering that there would be hydrogen coming off here. So we're going to look at the plane of our double bond coming through here like this. And so on this side of the double bond, we have two different substituents coming off. We have this one, and we have this one. This side is clearly bigger, so that's going to get ranked number 1 right here. This side is smaller, gets ranked number 2. And then on the other side of our double bond over here, we have a hydrogen on one side, and we have this carbon group coming off the other side. And so that carbon group is clearly larger. And so we can see that our larger groups are on opposite sides of the double bond, getting us to the last part of our name, trans 3-methyl-3-hexene. So we can see now that our naming is getting a little more complicated. These are all things that we have to keep in mind as we are naming various chemical compounds. Let's just see real quick where some of this alkyne chemistry, where some of this is important. One of the leading causes of blindness in people over 60 is something called macular degeneration. Patients that have this start to lose central vision but retain peripheral. It would look sort of like this. Now, when we look at the chemistry of vision in general, vision begins with a chemical reaction that's initiated by light. And so light comes into our eyes, and the retina contains millions and millions of what we call photoreceptors, things that are receiving the light. These are rods and cones that you might have heard about. The macula is at the center of the retina with a very high concentration of these rods and cones. What happens in the macula is that light is absorbed by something called rhodopsin, which converts a double bond in retinol from cis to trans. This changes the overall shape of a protein, which triggers a nerve impulse, enabling us to see. And so we can see here that this compound right here goes from cis to trans. And so that triggers a nerve impulse, which allows us to see, just that switching of that bond from cis to trans. In people with macular degeneration, the receptors of the macula eventually stop working, and so they will stop making that conversion, making that cis-trans conversion, which leads to not being able to see things in the center coming into those center photoreceptors, just from a simple cis-trans chemistry. And so some simple chemical changes can lead to big types of issues. Lastly, today, let's just take a look at something, what we call aromatic hydrocarbons. Aromatic hydrocarbons get their name because it was known in the 19th century that there were some hydrocarbons that were incredibly aromatic, very, very strongly scented. And they were found to contain a very unique unsaturated hydrocarbon ring. And so this 6-membered ring that we've talked about previously with alternating double and single bonds, that's an aromatic ring. One of the more common ones is called benzene. And it's quite often drawn like this because it turns out that these double bonds are what we call delocalized, meaning that they really sort of exist in the whole thing. They're spread out amongst all of these carbon atoms. And so this double bond, for instance, isn't necessarily found just between these two atoms. All 6 of these are spread throughout the whole entire compound. When we're naming aromatic compounds, benzene is the root name, and then we add the substituents coming off of that. So here's benzene. It's got a CH3 group coming off, which has the name methyl. So we get methylbenzene. Here we have a 2-carbon group coming off, ethylbenzene, and a 3-carbon group, propylbenzene. If there's only one substituent, we don't need to say where it's located. If there's more than one substituent, now we need locator numbers. The numbering begins at the larger substituent and then proceeds around the ring to get you to the lowest number. And so here we have benzene, we have an ethyl group coming off, and we have a methyl group coming off. The ethyl group is the more important one, and so we're going to number that as 1. And so we get 1 ethyl, 3 methyl benzene. We also have another numbering location that we use called orthometa-para. And so in that, what we do is, again, the more important group would get the sort of the main designation for a number. But then if your relationship is 1,2, like this example here, so in 1,2 dimethylbenzene, this could also be called ortho dimethylbenzene. In a 1,3 relationship, this would be meta dimethylbenzene, or a 1,4 would be para dimethylbenzene. Now, I know we're starting to get into a lot when it comes to our naming rules, so I want to point out, if you haven't found it already, when we go to our website, we go to the materials for hydrocarbons, and I think I also put the same sheet, let me double check, under the functional groups, which we're going to talk about next. I did. So this naming organic compounds handout. So again, you can also find it under the hydrocarbons materials, naming organic compounds. This is a handout that puts together all the different naming rules that we've talked about. And so it starts out just by talking about hydrocarbons. And so all the rules that we've talked about and we've used so far. So these are all the rules put together in one place, and then several different examples. And so I'd encourage you to start using this. Start looking at this if you haven't already. Go through the rules and see if you actually can make sense of all these examples too. Make sure you know why this is 2-pentine. Make sure you can come up with the name of this one, of 3,4-dimethylheptane, 4-ethyl-3-methylheptane. Again, making sure that you're able to come up with those same names. Trans 3,4-dimethyl-3-heptene, cis 3,4-dimethyl-3-heptene. At this point, you should be starting to get comfortable with coming up with some of these names. That's where a lot of the practice comes in. There are more practice problems here. Drawing some organic compounds, naming hydrocarbons. So a whole bunch of just different naming, coming up with the names for some of these compounds. Work these practice, use this handout, start doing a lot of practicing for these. That's how you're going to get good at it. And so that is all for today. Goodbye for now, and I'll see you in the next video.